Welcome to our last recitation, recitation 14 about integration. What I have for you today is problems about integration, problems of certain format that we haven't seen before. There's a lot of different types of problems that we can make about integrals, so I just wanted to talk about a few of them. So let's get right into it. Here is an integrable function f. This problem is giving you one integral and asking you for another. So suppose that the integral of f from 0 to 81 is minus 5. Calculate this integral from 0 to 3, but it's not quite f, it's this expression involving f. So of course, what you should not do is split up this integral as the integral of a product, because, well, that's not equal to the product of the integrals. You don't do that. Instead, what you should think about is when you look at this, the one that you want to calculate, you recognize that you have exactly the type of situation that you need for a u substitution. It's just that you don't see a full function in here. You don't see the expression for f, but you just see f of something, x to the fourth, and the derivative of that thing is outside, apart from a constant, x to the 3. So what you're going to do is, if you differentiate x to the fourth, you have 4 times x cubed. You want that 4 to be in there. So I'm going to multiply and divide by 4 like this. This is still the same expression. And now we can do this u sub u equals x to the fourth. What is going to happen with this? Du dx, as we just said, is 4x cubed, which means du is 4x cubed dx. That expression, 4x cubed dx, is right here. It appears there. So you can replace that with du. So let's do that. And what happens when we do u sub with a definite integral? You need to remember to change the endpoint of integration. In this case, you do it like this. When x, the original values of x are 0 and 3. When x is 3, u is 81. And when x is 0, u is 0. All I'm doing is looking at the relationship between u and x. U is x to the fourth. That's how I can discover corresponding values of u for each x. 3 to the fourth is 81. So this is going to become 0 to 81. F of x to the fourth is just f of u. And the rest of the thing in this integral, that's the thing that we just called du. So now we have this. And you go back to the problem. Initially, you might think, we actually don't know this integral. We know in the x variable, not in the u variable, right? This is the thing that they gave us in the problem. The integral of f of x dx is minus 5. But of course, this is now the same as f of u du. Remember that doesn't matter what kinds of substitutions you already did. When you look at an integral, you can always change the variable of integration to any name that you'd like. So this number that we just found here is the same as the integral of f of, for example, t dt. You could have written, or really any variable, x dx, for example, and it is equal to minus 5. Well, at least the integral part, together with the 1 over 4 outside, it makes a minus 5 over 4. So doesn't matter that initially in the integral that we want, we have an x. You might have changed this x to something else if you wanted, as long as you recognize that when you get to here, that's the same thing as this. So this was a u sub problem that did not give you a specific function. You can expect this kind of problem. It's very common. Let's do another u sub problem. This time it's indefinite. Compute this integral, and there is a suggestion. Start with u equals root of 1 plus 2x. And here is the novelty in this problem. We have not seen this before. Solve for dx in terms of du. Usually we see the contrary, but it's possible to do that. So let's see how this works. They're telling us try u equals 1 plus 2x square root. So let's try that. What is du dx? The derivative of the square root function would be 1 over 2 times the square root. But to differentiate this, remember you need the chain rule. There is a 2x inside, which is going to produce a 2 outside. And these 2's are going to cancel each other. So we are going to write du equals, what is that? Dx over square root of 1 plus 2x. Okay. Now, obviously, we see a square root of 1 plus 2x right here. That's going to get replaced with u. And then the problem is when you do this u substitution, you don't see this particular expression appearing anywhere in the integral. You see just a dx in there. So what we can do, this is what this hint here, the suggestion is talking to us about, solve for dx in terms of du. We can do that. Dx is equal to square root of 1 plus 2x du, which we can also write as u du. Right, so I just took this and multiplied over here to get this expression. And now I recognize that this square root of 1 plus 2x is the same thing as u. So that's why I wrote u du. Usually you don't see this step. Usually when you do du equals whatever, that whatever is already in there, except maybe for a constant, maybe like the 4 that we had to introduce in the previous problem. This time it wasn't quite there, so it was better for us to solve for dx in terms of du, because now we're going to just replace that with that. So what are we going to do? Once again in red here, let me leave this one in red. This one is going to get replaced with u. And I'm going to replace the whole dx up here with u du. What do we get? We get the integral of u du divided by, so downstairs we have a whole square root with a 5 plus, and then that square root inside is a u. I didn't mean to erase my red thing. Okay, so this is what you get after this first u substitution. So now let's work with this one. This is a simpler one. When you look at it, once again, you recognize that this is not a function that you can immediately integrate. You're probably going to need another substitution. And this is one of those cases where you have a sum or a difference in the denominator, and it's even under square root, like here. Usually you want to have that appearing in the numerator and have only one term in the denominator so that you can split the fraction. And in this case, it's pretty simple how we're going to achieve that by another substitution. This is one of the cases where you have a linear type of expression, like au plus b. In this case, just u plus 5. It's always useful to let things like that be your new variable, linear expressions. So 5 plus u, let me call that v. dv du is going to be just 1, so dv is equal to du in this substitution. And so what happens to this? So the du upstairs is going to just become dv, but what happens to the u? Well, how do we write u in terms of v? U is v minus 5. So this will go up here, and this du is just going to be dv. Finally, the 5 plus u downstairs is just v. So this becomes, let's see, u is v minus 5, du is dv, and then square root of v. So we can continue from here now. This is finally, let me just rewrite this so you can realize an expression that we actually know how to integrate. Because as I said, you're just going to split the difference in the numerator as two fractions, v over root v minus 5 over root v dv. So let's do this quickly. Each one of these is going to be a power of v. You have v to the 1/2 and v to the minus 1/2. Integrating powers is done by the power rule. You just add 1 to the power and divide by that same number that you just got. So minus 5b to the 1/2 divided by 1/2. There's going to be a plus c, but I'm going to only write that in the end after going back to the x variable. But these should be the antiderivatives. I'm going to simplify it just a little. Instead of dividing by 3/2, I'm going to multiply by 2/3. Always better to do this kind of step one at a time, very carefully. Like I didn't immediately go from here to here. Just to make sure that you get the right constants. All right, now we go back. First, you go back to the u variable. If you remember, v was equal to 5 plus u. So I'm going to replace v with 5 plus u. And finally, if you go back to the beginning, what was u in terms of the original x variable? It was square root of 1 plus 2x. Yes, so you finally replace that. And here, because we reached the function that we wanted in the variable that we wanted, this is now the final expression, and you have to put the plus c because this was an indefinite integral. That should be your answer. As a check, this is not a quick check, it's a long check. You have to take the derivative of this and see that you get the original expression. Try that, just to practice your derivatives if you want, but it's going to probably take a long time here. This is not a simple function to differentiate. I'm going to move on to another problem. This is a Riemann sum problem now. The function is this f1 over x minus 1 over x minus 3, and I have a graph below. I'm going to scroll to it quickly. Here's the graph. The interval is going to be between 6 and 15. This function is negative, but increasing, as you can see, as it turns out. So item A is compute the regular right and left Riemann sums, 3 subintervals on the intervals 6 to 15. So let me remind you what all of these words mean. First of all, regular means the 3 subintervals that you're going to be using will have the same length delta x. That is usually the case. And then right and left are talking about how you're going to select the sample point in each interval in order to form the Riemann sum. So what do we do for item A? Because it's regular, you should always start with calculating this delta x, the length of each interval, and that's very easy. B minus A represents the total length of the entire interval from 6 to 15, and n is the number of intervals, which they said should be 3. So in this case, that will be just 9 over 3, which is 3. From here, you can get the points that you want, the form, the partition. We're going to have 4 points, and they go from 0 to 3 in the indices. That's usually how we do these things. Just remember, it works like this, right? The 0th point is the initial point of the interval, and then each point is obtained by adding a certain number of interval lengths, delta x. So in this case, you start with a 6, and then you add 3, which is delta x, to that to obtain 9, and then 12, and the last one should be 15. It's the same thing as the b. So I hope this is intuitive enough. If you're going to divide the interval between 6 and 15 into 3 sub-intervals, then the breakpoints will occur right here, 6, 9, 12, 15. Let's go ahead and draw them up here so we see things happening. That's not a good location for 9. All right. Now, this function is actually below the x-axis, so it's not the, what we are talking about is not the area, but it's the negative of the area. But below each one of these intervals, there's going to be a rectangle. The height of the rectangle is determined by the value of the function, but on a specific point, that's going to change depending on whether you're talking about the right or left. So now if you want to talk about the right sum, let's do right sum first. What it means is that you need to select the right endpoint in each interval. So for example, in the first interval, you're going to select f of 9. And then for the second one, f of 12. For the third one, f of 15. And you don't really need the drawing to see this. You can just say the right sum. Let's call that like R3 because there are 3 intervals. How does that work? You're going to do delta x times f of the right endpoints of each interval. So you just do this calculation. Delta x is 3. And then f of 9, how do we know that? You just go back to the function. F of 9, 1 over 9 minus 1 over 6. We have the expression for the f, right? So you just calculate this. I have the answer here that you can check. Should be minus 1 over 10. That's what R3 is. And I'm just going to draw it up here so we can visualize it. Once again, this is not part of the solution. In green, let's say. What is happening is that for the first rectangle, I'm selecting the value of f of 9 to give you the height of that rectangle. So it is right here. For the second one, I'm selecting the value of f of 12. So it's a slightly shorter rectangle. And for the last one, f of 15. The sum of the areas of these rectangles should be 1 over 10. Areas are always positive, of course. But the Riemann sum itself is negative because the value of the function is negative. So minus 1 over 10. This is the right sum. How does the left sum work now? What changes? Same delta x's, but now we're going to be looking at the left endpoint. So 6, 9, and 12. I'm going to start by drawing that in here now, maybe in blue this time. The value of f of 6 will be selected for the first rectangle, f of 9 for the second, f of 12 for the third. So if you now draw these rectangles, you see that they are taller than the right sum. We should get a value now that is more negative, right? We got minus 1 over 10 for the first one. This one should be a smaller number, or a number that's more negative. Like, for example, minus 2 over 10 would be a possibility. But we'll see what will actually happen. What is L3? So delta x times f of 6 plus f of 9 plus f of 12. If you work this out, you're going to find minus 1 over 4. Yes, which makes sense. All right, so that was item A, just calculating these two Riemann sums. Let's work with B now. Without calculating the integral, this integral, the integral of the function f between 6 and 15, can you say whether the Riemann sums above are larger or smaller than this integral I? So that goes back to my drawing here. We can see from the drawing, the right Riemann sum, in this case, it is also an upper Riemann sum. That's because the function is increasing. So when we took the right Riemann sum, that was the shorter rectangles, by the way, you can see that each one of them stays entirely above the graph of the function, like the first rectangle here, entirely above this piece. That's because the point that we selected for that rectangle, f of 9, is the largest value of f on that piece. So as I said, it's the right sum is also an upper sum in this case because the function increases. So this gives us a hint for how to answer B. Because f is increasing, as we could see from the graph, Riemann sum R3 is also an upper sum. So larger than the actual value of the integral, which we called I. So the right sum should be larger. The number minus 1 over 10 is larger than I. And similarly, The left sum, L3, is also a lower sum. So lower sum is also smaller, always smaller. All right, so just be careful that this is not always the case. Just because the function was increasing, we could have this relationship. Right sum is upper, lower sum is lower. In general, they're not going to be equal to each other like this. You could have a function that increases and decreases, and maybe one of your subintervals occurs right there. So you can see that the upper sum would include this value, but the left sum would include this value. The right sum would include this value. They're not related to any one of the others in general. Okay, but this answers B, but now C is just fundamental theorem of calculus. Compute the integral, compute I using the fundamental theorem of calculus, this integral. So from 6 to 15, 1 over x minus 1 over x minus 3. That should be an easy one. How do you calculate integrals using the fundamental theorem of calculus? Look at the function, try to find an antiderivative for that, if one is readily available. Otherwise, you may want to try use substitution. In this case, that should be very easy to do. A function whose derivative is 1 over x is ln of absolute value of x. Though we don't really need this absolute value here, I'm going to erase it because the interval of the integration is already all positive numbers. X is a positive number here. All right, so this is ln x, and then minus, you can check that ln of x minus 3, the derivative of that is this. Be careful that in general, when you try to integrate 1 over something, in general, it's not as simple as taking ln of that thing or with absolute value. In general, that's just not how it works. When you differentiate this, you usually don't get that because of the chain rule, because derivatives of this function f also appear. But in this case, the function that we're talking about is x minus 3. That works, right? What happens when you differentiate this by the chain rule? The thing that you multiply by is just a 1, so it gives you what you want. All right, so that was easy. What do we do with this function, this entire thing? We calculate between the two endpoints, 6 and 15. What does that mean? It means calculate the function at the number 15. Here it is. And then subtract the same function at the number 6. Here it is. This is already good enough as your answer, although you know how to simplify logs, right? This is going to be a bunch of sums and differences of logs, so you can put the factors with a plus inside of the log in the numerator. The 15 and the 3 have a plus accompanying them. So that would be 15 times 3. The others, the 12 and the 6, have a minus. You can put them in the denominator, and this simplifies as, let's see, 15 over 24, or also 5 over 8. This should be the value of the integral. As a quick check to see that you get the right answer, we know that whatever this value is, it should be negative because the function is entirely below the axis. So you know that the integral represents the negative of the area between the x-axis and the graph. And the number that we got is a negative number. ln of anything less than 1 is negative. So this is good. Another check you could do is to verify really that this number is between minus 1 over 4 and minus 1 over 10, which were the Riemann sums, the right and left. As we argued in item B, it should be between the two numbers. You need a calculator to see this, but it's true. So just to check that you have the right answer. But I'm going to move on now to the next problem. Here is one that uses the different properties of integrals. Suppose that you have two integrable functions, f and g, And I'm giving you the value of lots of integrals in here and asking you for another one. So let's see what we have here. What we want is the integral of g between 1 and 0. They're giving you this integral in the unusual order, the larger number downstairs. But you know how to work with this, right? You just introduce a minus sign to flip the endpoints. And what do we have? Okay, the first two that we have are integrals for f, and one of them is from 0 to 2, the other is from 2 to 4. So you already know that those two together will allow you to get the integral of f from 0 to 4. We're going to start with that. Then we have this crazy thing here. It's an integral from 0 to 4 involving f and also g. Because we just discovered integral of f from 0 to 4, you're going to be able to find for g from 0 to 4. And then finally, they give you g from 1 to 4. Together with what we already discovered, should be able to give you from 0 to 1. That's the pathway to finding this. So I'm going to write all this down now. So first of all, the integral of f from 0 to 4, we can find that by adding these two together in this, I shouldn't say order, but like the order of their endpoints. This is one of the theorems that we have. If you want to integrate from a point to another, you can always start from that starting point and stop somewhere, and then go from that somewhere to the endpoint that you want. Integrals have this property, and those two are integrals that we know. That's -3 and -5, so -8. So we keep this one, and I'm going to work with this third one here. They're saying that the integral between 0 and 4 of this linear expression between f and g is equal to 28. I can split that up like this. Integration is a linear operation, which means exactly this. I forgot a dx here. You can split the integral over this difference, and then each one has a constant in front that can go outside of the integrals. So that entire thing is the same as I just wrote down here. All right, this should be 28. But now you see here the integral of f from 0 to 4. We just found that. That's -8. So 4 times -8 minus 3 times the integral of g from 0 to 4 is equal to 28. This equation is going to allow you to find this integral of g. Because now move this -32 to the other side. It makes a 60 together with the 28 plus 60. And I'll divide by -3. So -20. That's the integral of g between 0 and 4. Now I'm going to continue here. Why was this one useful? Well, now g from 0 to 4 is known, and we also know from 1 to 4. So you should be able to find from 0 to 1 by writing this. The integral between 0 and 4 is the same thing as between 0 and 1 plus 1 and 4. 0 to 4 we just discovered. That's -20. 0 to 1 is kind of what we want. 1 to 4 was given in the problem. Let me look up there. 1 to 4 for g is the number pi. So from here, you can find that the integral between 0 and 1 is -20 minus pi. That's not really the one that you want. The problem, for whatever reason, wants it from 1 to 0. So that was the last of the properties that I wanted to mention about integrals. It's that when you flip the endpoints of integration, by convention, by definition, what it means is just introducing a minus sign in front of the integral. So, and this one is the one that we know, -20 minus pi, together with this outside minus will make 20 plus pi. Should be the final answer. Okay, so just using properties of how to sum and how to combine integrals over different intervals. Just be careful about the order. Moving on. Okay, the graph sketching problems. So suppose that f is a continuous function with a domain from 0 to 5. Continuous is going to be important, by the way. And f of 0 is minus 2. Let's keep that in mind. Suppose that f is also differentiable on essentially all the points here except for the endpoints 0 and 5, as well as the number 3. We see that this in interval notation here, we're splitting the interval into two pieces without including the number 3. So the function is not differentiable at 3, and the graph of f prime is sketched below. They're also saying the second part of it is a half circumference. So this part. I'm going to scroll so you can see the graph. The question is sketch a graph of f, indicating the values of f of 1, f of 2, up to f of 5. So what's going on? Well, first of all, you see the graph of f prime here. As you can see, it's undefined at the number 3, as it should, because they told us the function f is not differentiable at 3. So that means f prime of 3 does not exist. We've seen problems like this before, where they give you the graph of f prime and ask you to sketch the graph of f. And we've also seen how f prime determines the shape of f, but the values of f could really be anything. Now they are asking for values for f, and the extra information that they're giving us is certain areas. Look at this. This area is 2, this area is 1, this area is 4. This area is not given, this one, but we can find this quickly because they told you this is supposed to be a half circumference. So actually, let's start by writing down these areas here, all 4 of these. What is the radius of the circumference? If this is the center right here, this is the radius. The radius is 1. So the area of the whole circle would be 1 times pi, so pi. This quarter circle then should be pi over 4. Similarly for here. That's simple geometry. And well, the areas below here, those are squares. They don't look like squares, but they really are. Look at this. From 3 to 4 is a length of 1. And what is the height? Well, we can see right here, this number is also 1. So 1 by 1 squares. Okay, now we have all the area information that we need. This, by the way, also very common to see problems where the shapes of certain segments of the graph are simple geometric figures like circles and straight lines, and they allow you to find certain areas. Okay, so what are we going to do here? First, the usual things. When f prime is positive, that is the same thing as f being increasing. When f prime is negative, that's the same thing as f being decreasing. We've studied how this is essentially what the derivative is. The derivative is the slope of f. But there is also a relationship to concavity. When f prime is increasing, f is concave up. And when f prime is decreasing, f is concave down. This is our definition of concavity. You know that concavity is also determined by the second derivative, but this problem did not give you a second derivative, so we work with the first one. So be careful about the things that you're looking for in this graph of f prime. Positivity versus negativity, but also increasing versus decreasing. All right, so when you look at this graph, you realize that the locations where it changes behavior are just the numbers 0, 1, 2, 3, 4, 5. So I'm going to go ahead and imagine a line like this, 0, 1, 2, 3, 4, 5. And try to imagine the shape of the f function in each one. Between 0 and 1 in here. f prime is positive, but it's also decreasing. So f should be increasing, but concave down. An increasing concave down function looks like this. And that's what you need to do for each one of these pieces. Actually, the same thing happens between 1 and 2. Same shape. So it's actually just going to be one entire thing, a continuation of the same shape. As you can see, the function f prime is still positive and still decreasing here. Now something changes between 2 and 3. Still decreasing, so it's still concave down for f, but now it's negative, which means f is decreasing. A decreasing concave down function looks like this. And now suddenly there's a change in the two things. Concavity will suddenly become positive because this is increasing, and f is suddenly going to become increasing because this is positive. So now a positive, increasing concave up function. That should be the shape. Yes, and then finally for the last one, same analysis. Increasing, but now concave down. Right, so we have the shapes of the function. Just try to imagine those put together. But there's one more thing now, that the values of f. This time we are able to find the values, these values, on the each one of those numbers. And it's going to be by using the areas. How does that work? So you have the fundamental theorem of calculus, which you can write in this form. Remember, this is one of the forms of it. It says that whenever you're integrating a certain function, the certain function in this case is f prime, all you need to understand is an antiderivative of it. An antiderivative of f prime is f. If you have an antiderivative, you just calculate it between the numbers b and a, whatever this b and a are. We're going to be applying this for many different values of b and a. Why is this useful for us? On the one hand, the right side here gives you values of f, rather differences of values of f. So if you already know one value to start with, let's say you know f of a for some point a, then you can also find for the point b, as long as you understand also what this left side is. And what is the left side? Well, integrals involving f prime, they are areas. They are going to be given by the areas in the graph. So I'm going to start with the first one. The first useful points a and b to select are going to be 0 and 1. Why? Well, this one, f of 0, we already know. They told you it's -2 in the problem. F of 1, we don't know. We're going to find it from this equation. What is the integral of f prime between 0 and 1? Scroll back to the graph of f prime. That integral represents the orange area here, the 2. Remember, this red graph here is the graph of f prime. The integral between 0 and 1 represents the area. Negative if that area is below the axis. Positive if it's above. In this case, it is positive. So +2. This is now an equation for f of 1. What we have here is 2 equals f of 1 minus -2. Don't forget this minus that came from the fundamental theorem of calculus, together with this other minus that was just the value of f of 0. So this makes a +2. On the other side with the other +2 makes a 0. F of 1 is 0. This is how we can discover the values if you know one value to start with, which was f of 0, and you know areas of the f prime function. So what we have to do now is keep applying this between any two consecutive numbers. Like the next one that we want to find is 2, f of 2. So you can start by writing this, the integral between 1 and 2. We know that from the graph, that's 1, +1. F of 1 we just discovered is 0, so this is going to give you f of 2 equals 1. Similar process. By the way, you could also have integrated from 0 if you wanted. Instead of 1, this would have been a 0. it's going to give you the same answer, obviously. The only problem is when you consider the integral between 0 and 2, look back in the graph, that requires taking two different areas into account. Between 0 and 2, the area would be 2 plus 1, so 3. Of course, it's not that difficult to do, but in general, you want to simplify your life. You want to just consider points between which you only have one area to consider. All right. But we can find now the other points. The integral between 2 and 3 is equal to f of 3 minus f of 2. F of 2 we just found is 1. What is the integral between 2 and 3? I'm scrolling back up once more. The integral between 2 and 3 is this area, but now it's negative because it's below the axis. So it should be a minus 4. And here you have a minus 1. If you move to the other side, makes a minus 3. So f of 3 is minus 3. This is how you find the other points, by the way. What is f of 4 and f of 5? They're going to be minus 2 plus pi over 4 and minus 1 plus pi over 2. Same process. Remember that the areas that we need for these ones we found in the beginning. Like now that you know f of 3, how you're going to find f of 4? Well, you're going to utilize this area. The entire area below the graph, right? Don't consider just the pi over 4 part. You also need everything below the graph up to the x-axis. So pi over 4 plus 1 in this case. And you know how the other one will be. This one. Okay. So we found all the values of the function, as well as the shape between each one of those values. That should be enough to sketch this graph. So that's what I'm going to do here. You should be looking back at your own notes for this, just so you, I'm not going to scroll back up anymore, but so you realize that these really are the same points that we just discovered. So I'm going to mark down 1 minus 2 minus 3. 1, 2, 3, 4, 5. Start by marking down the values that you just discovered for the function. We know f of 0 is negative 2, f of 1 is 0, f of 2 is 1, f of 3 is minus 3. F of 4 was some number involving pi that you can see is a negative number. Similarly for f of 5, but that one is positive. Okay. So the graph has to go through these points, but obviously you don't just do straight lines like this because that's not what it is. You have better information. You have the shape of the graph, concavity and also increase versus decrease. Well, the increasing, decreasing behavior is determined by these points, right? Of course, it can only decrease between 2 and 3. But like, is it concave up? Is it concave down? That's important if you're sketching a graph as accurately as you can. So remember, it was concave down all the way between 0 and 3. You have to draw a concave down shape going through these points. I'm going to cheat a little and bring this one a little bit down so we can really make sure that our curve looks concave down. It should have a horizontal tangent line at the number 2 because f prime of 2 was 0. So I can do a little bit better. Make sure this one has to be a horizontal line. All right. And then it goes all the way down to this number. Now the function is continuous. Look that there is a value for 3, even though f prime of 3 did not exist. F was continuous since the start. So we have to continue from this point now. And how do we continue? It should be concave up between 3 and 4. And then between 4 and 5, it becomes concave down again. You see, up is this shape, down is this shape. So this is more or less the graph that we wanted to draw. And here, a horizontal tangent line.
You can see there's a cusp here. It looks like this. So not differentiable at that point, as we already knew should happen from the graph of f prime. F prime of 3 does not exist. All right, very good. So the only new thing about this problem was discovering the values of f based on the areas for f prime. That's the fundamental theorem of calculus. And I have just one more problem here. Verify that the function is a solution to the initial value problem. Remember, the initial value problem is something like this, where you're trying to find a function, g in this case, and you're given its derivative, and you're given its value at a certain point, and you want to find that function. If I just gave you this problem and asked you to solve it, that would be a very different problem, a kind of a difficult one, because, well, you know, how do you solve an initial value problem? You look at the differential equation, and you say g should be the integral of that function that you see, minus sine x over 1 plus cosine square. Well, what is that? I don't think we know how to integrate this function. Maybe if you simplify this a lot, you can try to be creative here, but like u sub is not going to help you. The thing that you see in the numerator is not really the derivative of the denominator, for example. So it's just not going to be very easy. But fortunately, this is not what this problem is saying. They did not just give you the IVP, they gave you the solution. And they just said verify that it is a solution. That's a very different thing. If somebody gives you the solution and asks verify, what do you have to do? You just have to show the calculation for g prime, look at this g, calculate g prime, and see that you get this. And then also verify the second equation, which is called the initial condition. So calculate g of pi over 3 in this formula. See that you get 4. That's what you have to do. So we're going to start with g prime. What is g prime? Here is g again. How do we differentiate this function? The 4 is the easy part. That's just a 0 for the derivative of that. But you have to differentiate now the integral in the x variable. This is now fundamental theorem of calculus, first form, the one that says how to differentiate functions with respect to a variable that appears in one of the endpoints. So how does this one work? Well, you have the x downstairs and it's in a function, secant of x. What you have to do is you have to consider the area function for this particular integral, maybe call that a. Let's say from 2 to x, where x should be in the upstairs, at the upper endpoint, and then we selected the same 2 to be the lower endpoint. If you consider this area function, the fundamental theorem of calculus says that a prime is equal to, what is it? If you have a function where downstairs is just a number and upstairs is just x, the derivative is the function inside of the integral, just calculated at that x. So 1 plus x squared. Remember that this dt upstairs is the same thing as 1 times dt. So you can really see this 1 over 1 plus t squared is the function being integrated. That's the function that we plug x into. So this was fundamental theorem of calculus. The g prime that we have up here, it is not the derivative of a itself. This is not a, but it's a related thing to a. First of all, if you flip the integral, then the secant will go up and the 2 will go down. So introducing a minus sign for that. And then you see that what you have is actually a of secant. Just imagine this integral with the 2 endpoints flipped. So you have the 2 downstairs, and upstairs you don't have x, you have secant of x. So that's what a of anything is. Okay. So you can see from here that chain rule is going to be needed. This is always the case, by the way, when you're differentiating functions that have other functions as endpoints of integration. So what is the chain rule going to say? That this should be, I'm going to do it in here. What is the derivative of minus a times a of secant? So you need minus a prime of secant times derivative of secant, which is secant times tangent. This is one of those that we should memorize. Okay, so what is a prime of secant? According to the formula for a prime, that's the one that the fundamental theorem of calculus helps you with. A prime of anything is 1 over 1 plus that thing squared. So a prime of secant is 1 over 1 plus secant squared times secant times tangent. This is the derivative of the g function. Look at where we started. A g prime is equal to this. Well, we would like to verify that it's equal to actually this. It doesn't look quite equal, but it's going to be. It's because this is given in terms of sines and cosines. So what we have to do now is just simplify this trig expression and see that it becomes sines and cosines exactly what you want. So like the secant times tangent is the same as 1 over cosine times sine over cosine. And here 1 over 1 plus secant square. That's 1 plus 1 over cosine square. After you add those two fractions, you get this. Just replace secant with 1 over cosine and simplify. This is what you're going to get. I'm going to write the reciprocal of this fraction. And you see that the cosine square will cancel with these guys. So this simplifies down to just minus sine over cosine square plus 1. Check. This is exactly what we wanted to verify that the g prime function is equal to. So we have verified that the first condition is true for the particular function given. What is left to do now is verify the second. Is g of pi over 3 equal to 4? Once again, for this function g. So what is g of pi over 3? 4 plus, you plug in the pi over 3 right here and the location where x was. Right, g of x was equal to 4 plus integral of secant of x to 2, and then t is just a variable of integration. So you plug pi over 3 right where x was. So this is now just something that you have to compute. This integral, by the way, we don't know how to calculate the integral of 1 over 1 plus t squared in this course. It's the arctan function. But we don't have to because, as it turns out, secant of pi over 3 is exactly equal to 2. Just verify that. Secant is 1 over cosine. Cosine of pi over 3 is 1/2. So the secant will be 1 over 1/2, which is 2. And now, okay, doesn't matter what the integral of this function is. What happens if you integrate from 2 to 2? Just 0. So you're left with just the 4 part. And this checks. You do have g of pi over 3 equals 4. That concludes the problem. So you might see this in the future in homeworks, or I don't know. Somebody is giving you an IVP, but they don't ask you to solve it. They say verify that this is a solution. So what you have to do is just calculate the derivative of the function given, and then also one specific value of it. If it checks with what they said it should in the IVP, then it is the solution to the IVP.